All right. Welcome everyone to our first panel. Again, I'd like to reiterate how happy we are to have everyone here. We have a full house, if you can't see behind the camera. We also have a booming audience on the internet. This is being streamed. So with that, let's kick off the panels. I am the CSO at Lagrange. We have our distinguished guests, and we were also lucky enough to have the panel from Ismail just before this, which covered a lot of ground in terms of some of the topics that we want to discuss on stage today. What we'll do is we will do some deep dives into a lot of the topics that Ismail mentioned, particularly on verifiability, when it comes to AI and when it comes to ZK and how these concepts are related. We'll get into a little bit of detail as to what the architectural differences are between trying to look at the foundation of an AI model and a foundation of an AI model that's wrapped in a cryptographic scheme. And we'll see that some fundamental trade-offs have to be made in order to accommodate these technologies. We will see and we'll hear from our panelists how they think about these trade-offs. Ultimately, we are limited by practicality. We want to build systems that aren't just interesting, but are useful. We will see how some of these trade-offs manifest, both from an economic perspective and from a technological perspective. Before we do that, we want to lay some groundwork to make sure that we really understand what we're talking about, which I think is a very good idea in most cases. Verifiability in AI, verifiability in ZK, and just verifiability of a computation. What does that mean? What does that mean?
So it is being able to say with certainty that a particular computation, inference, or something came from a certain source, whatever it is, right? It could be a model, it could be a deterministic program, it could be anything. Just being able to say with certainty that this output came from this program or input.
I think there's one more point, which is training itself. Model is as good as it's trained on, the data it's trained on. So you want to make sure that whatever model is being claimed that it's supposed to be unbiased or whatever, you have to also make sure that the data that's being fed was the right data that you're looking for. So verifying the training aspect as well. And the second thing, many of these models these days actually have external data, so it's not static anymore, of course. So they actually feed into external data, and the data that you feed as a consumer, and making sure that those data that is coming in as well from external sources is also impacted in a certain way. So verifying that as well. And then, of course, the classical, which is compute and inference.
I think test. I think historically, verifiability has been thought about in two forms. There's data and there's logic. Cryptography historically has done a really good job at ensuring verifiability of data. And for instance, we have now hash functions and commitment schemes for that. It's only very recently that modern computing has made verifiability of logic become more practical. And now you're starting to see that, for instance, with zero-knowledge proofs. This is stuff that can now be computed on CPUs. And I think ultimately you need a combination of both the data and logic to be attestable and verifiable, meaning it has to be claimed to have the right provenance, and it has to be computed actually in real time to demonstrate that the, in this case, in the AI case, the inference was actually done correctly.
So I think my role here is to take a slightly different take in definition of verifiability. As some of you probably know, Layer builds this thing called Waves. We work in kind of the EigenLayer AVS ecosystem. AVS used to stand for something different, but now it stands for Autonomous Verifiable Service. But it means verifiable in a different cryptoeconomic sense. It doesn't necessarily mean it in the ZK sense, but it does mean that there's a cryptoeconomic underlying trust assumption that has different applicability than, say, a ZK trust assumption. It also has different performance requirements. So I think part of our thesis with this is that there's some limit, there's some computational limit that is probably not at computing every single thing or ZK proving every single thing in an LLM training run. That seems computationally too intense to do. And it probably isn't something very, very small that's easily ZK provable. There's some other cryptoeconomic trust model that fits in somewhere that has to do with AI. And it's something that we seek to support as a core part of what we're doing. And I guess one challenge I would have for the rest of the panel too, as we think about this, is like, what is that limit where ZK is running up against performance requirements? And two, one thing we're thinking a lot about is deterministic AI and using basically cryptoeconomic trust plus consensus to be another form of verifiability.
Excellent. You skipped to one point of logic that I really wanted to get into, which we were going to talk about later, but who cares? We're on stage. We can talk about it now. I'm actually going to tell you a very short but real story that came well before ZK and AI, and you'll see why it's particularly relevant but also very amusing. So I had a friend who shall be unnamed who used to work with national labs doing computation. And the problem that they ran into was actually very simple. They were doing some calculation. You can just assume it had to do with, let's say, weather modeling. Okay, it was a simple physical deterministic model for all intents and purposes. Deterministic just means we have the governing equations, assuming that you can partition the grid in space and time with infinite precision, or the amount of precision that you need. There is no reason that you shouldn't be able to come up with the same answer on any computer at any given time, right? These are simple equations of physics. The only issue that he had, or rather he didn't have, was security clearance. So he was not actually privy to the details of the model whose solutions he was using. This is actually very normal. If you do anything in defense, if you do anything in aerospace, if you do anything that's even proprietary information, it's very normal. If you use, if you've ever done any applied mathematics or engineering work, many times you will use off-the-shelf private software for 3D modeling, for even for architecture. You're not actually privy to the source code by design. You're only running the executable. You give it the input, it does some stuff, it generates a logo that says I'm thinking, and sometimes, and in his case, this was not just minutes or hours, this was days. So you'd have to wait days until the computation is done. And all you'd get out is a CSV with numbers that says this is the output, okay? If you know anything about that modeling space, you'll realize that A, this is a very iterative, long and buggy process, and B, you fundamentally don't know what's in the black box, and that's by design. But there was a saving grace. And what was the saving grace? The saving grace was these black boxes had to follow one simple rule, and that was the laws of physics. In physics, you have conserved quantities. You know that no matter what happens inside the box, no matter how outlandish, it has to follow simple laws of physics. And so ultimately, that's what he ended up doing. Even though he was not privy to what exactly was going on in these simulations, he could, at the end, do a much simpler calculation to verify that whatever was done inside the box simply did not violate the laws of physics. What is the mechanical equivalent to that when it comes to the architecture of transformers? And how do we think of it from the perspective of ZK in particular? Was that analogy clear? I know this is a bit of a toss-up. In any particular order?
For me, in the end, everything is a compute, right?
Go on.
Everything boils down to either building a Boolean circuit or building an arithmetic circuit, right? Everything boils down to that. And this is the power of ZK, which basically says that, no matter what you circuit it, you will be able to build this. You will be able to build a protocol that allows you to prepare or produce a succinct, very small proof that can be verified, without actually having a very huge compute capacity. So that's a theorem that basically says that you can actually do it for any arbitrary program, as long as you can convert that into arbitrary circuit or arithmetic circuit and so on. So for me, it's like, as long as you have this ability to take this program or circuit, then you would be able to prove anything in a meaningful way.
So before I let you go, again, a topic that we're going to jump right into, but I can't leave you here. What if it's non-deterministic?
This is the tricky bit, right? Which is this is a tricky bit. So assume, and if you have non-determinism, it makes things a lot more complicated in many settings, and that's the challenge. I don't have a good answer to it. But at least if you have deterministic models, then it'd be much easier to. But again, most of the models today that you use are all non-deterministic.
I think, when we talk about circuits, to the analogy you just drew, it's basically about saying, am I constraining the space sufficiently? And I think when it comes to circuits, you're basically, you can under constrain, you can over constrain. Over constrain means you end up losing on performance. Under constraining means you give too much of a freedom of movement, meaning you enter into non-determinism potentially. And I think that this is where, if your model's not sensitive in and of itself, like if it's just publicly known, then you can always, for example, encode as hard-coded constants into your circuit the actual weights that you want to apply. And this would give you probably the safest guarantee in terms of performance. It also gives you kind of the best performance because the constants end up being free, but you end up with very limited range of freedom. So you end up in a truly deterministic space, but you have kind of no range of movement as well in that.
If I may add to this, talking about physics, right? Of course, ZK and cryptography have certain limitations, right? But talking about physics, you actually, and there are people building this, you could imagine things like physically unclonable function-based chips. So you would not necessarily prove that the mathematics going in there is actually correct, but you would be able to, assuming it's a non-deterministic model, but you would say that whatever is running there, it's actually valid because of this fact that the machine is not tampered with. So you could actually build, I'm not saying Intel SGX, but you could imagine Intel SGX-like chips where the chip is replaced by a physically unclonable function, then you actually have those guarantees that you could get. But again, it's not the same thing as ZK.
Can I take us a step back? Sorry. So, just so we clarify the question, what are we trying to verify and why?
So I suppose this is the perennial question. There are different layers when we talk about verifiability. We can talk about the model itself. We can talk about how the model was calibrated. I know in this space we like to call it how it was trained. These are ultimately calibrations. And we know, like you said, when we talk about calibrations, we're really talking about hidden constraints. They show up or they manifest in the calibrations, but that's what it is. And the interesting bit with LLMs is that I'm going to diverge. I'm going to tell you another very short story. And it's the story of the coin flip. When we talk about probabilities, we always talk about, in the most introductory form of probability, we talk about coin flips, right? It seems like an odd notion if you think about it. A coin is not so different than a ball, and it's not so different than a point object in space. These things, as far as I know, they follow Newtonian mechanics, and there shouldn't be any reason why simple laws of motion govern coin flips. So I have a coin, it's set at an initial angle in three-dimensional space, and I perturb it. I put an initial perturbing function, and then I simply model its evolution in time, and I can tell you 10 out of 10 times whether it's head or tails. But that seems incongruent with reality. Why is that? It's metaphorical. I'm going to tell the answer immediately. The answer is the model is extremely sensitive to initial conditions. And so even though we are talking about something that is completely deterministic, it is so sensitive to perturbations on the numerical scale. So even if I try to simulate this on a computer, it is so sensitive to the machine precision of the instrument that I'm using that I'm better off talking about it in the context of probabilities and not using deterministic equations. So the reason I went on this tangent is to talk about the third layer, which is the input. Now, what do we know in this space that is extremely sensitive to the input? LLMs. LLM prompting is highly sensitive. In principle, there should be no reason for me to try and predict the output of an LLM based on the input. However, because of the nature of the interpolation that's being used, remember, LLMs predict on a token by token level. They are trying to literally predict the next word, the next set of characters. They're not trying to solve a coherent set of logic. Instead, they're literally trying to predict the next character. And so that ends up being, funny enough, very similar to the coin flip problem, in the sense that in principle, we can do it. In practice, it is highly sensitive to the perturbations of the input. How's that?
That's great. So as you say, right, I think verifiability or all of this comes in different flavors, and it's also a spectrum, right? In a lot of cases, what we're really trying to do is we're actually looking for explainability more than verifiability, right? If a model does something, it gives a certain output. We want to understand why it's actually given us that particular output. Now, in terms of with transformers specifically, going back to your initial question, given transformers are becoming more and more complex, and we are actually getting into these reasoning models and all that, with everything that's happening, the internal circuitry is getting so complex that it is going to be extremely hard for us to actually lift the hood up and say, this happened because of this. And I think determinism is completely out of the window. So we really have to think about, if you're really going down the path of explainability, how can you do that? Especially now, because there are many instances, I'm sure all of us have read this recently, especially from the Claude red teaming team, that models are getting very sophisticated at lying to humans, right? They are starting to hide their true intentions. And why they're even doing that, nobody understands. And it could be because of biases coming from data coming from a human world. But it is becoming apparent that it is very hard to go back and verify or explain why models do certain things, because they're going to lie to you right straight out of the back. Now, I think some of the approaches that are being proposed now is you actually create another model, which is like a psychologist, right? Pretty much the way you understand why a model does something is akin to the human brain, because you can't just look at somebody's brain and understand why and what the true intentions of a particular person is. So you actually have to use methods like psychology to get to the bottom of things. So what's starting to happen, and new research is going down this path, is you're getting new models which actually try to understand what other models do. And explainability is going in a particular direction. I think in my understanding of verifiability and how I sort of map it in my mind is, once you have a model and it gives you a certain output, and there are many models which give you different outputs, how do you verify where that came from? Which output came from which model? Or, for example, which data set was used within that model to give that particular output? What do you think?
So
Please go ahead. I'm not trying to hog the panel here.
So I just wanted to take that in a little bit different of a direction, which is that there are lots of reasons why we want this non-determinism, and we want the temperature of the system and the variability of the coin flips to turn up. But there's also a whole set of use cases of this technology by turning it down to zero, like governance, for instance, where we want it to produce exactly the same output. So the same hardware, exactly the same hardware, the same exact model of GPU with exactly the same seed, with any variability turned down to zero, will produce the same output, right? And so for things like governance, where you really care what that system outputs and you want it to be able to be predictable, like there's a use case for that too, which is what we're focused on. But I agree with everything said as well.
So keep it there. Then let me ask you this. You seem to always be peeling the right layer of the onion. Is explainability or are explainability and verifiability, are they mutually exclusive? And let me one more story. When we started to, first of all, everybody here has a phone. If you get on your phone to go to chess.com and you turn that baby to 100 and you try playing against the best form of AI, it will absolutely smoke you. It'll basically smoke everybody. It's not even close. Okay. It turns out there's a reason for that. And that we crossed that chasm when we basically stopped trying to understand how the machine was reasoning about the chess moves. We basically gave it free rein. We removed the constraint of explainability completely. All of a sudden, it went from being a really, really good but interpretable, high-ranked ELO player to a god. Okay, the best chess players today and in history can't even hold a candle to a model that doesn't care about explainability. So in that regard, performance, or verifiability in some sense, and explainability seem to be somewhat exclusive, at least. Back to you.
It seems like there are a lot of reasons why you would want explainability, but it doesn't seem like a necessary precondition to verifiability in all circumstances. So you could verify behaviors of the system proven on the circuits, proven on the math of the system without a human being able to understand what it does.
Well, the way I see it, the better that the more that we can reduce the overhead from the ZK side and from the LLM side in general, in terms of verification, the more we can push the envelope when it comes to explainability. If the overhead is so large, we just have to basically throw our hands up and say, I'll take what I can get, because the performance is so poor if you try and do it in a matter that's explainable to me. The more we can reduce that overhead, the more bandwidth I have for pushing the envelope and saying, go crazy. What are the bottlenecks today on the ZK side that are not allowing us to push that envelope?
One is the models are too big. Models that are realistically used in practice, they're way too big. And you could compare that with systems like EVM or so on, which is much, much smaller. Even then, that is still quite expensive. And so if you're thinking about, hey, can I get the entire LLM under O1 model or whatever model run by OpenAI, that's not possible. And even if you could somehow make it happen, it's going to take you some time before you get the proof. By the time you probably have moved over, right, as a user. So that's one of the biggest challenges, which is compute is way too intensive and the circuitry is way too expensive to produce ZK proofs.
I would even layer it on one step further from your point of, asking the question of what is the most efficient way to represent your model today in a ZK circuit. I think there's been multiple approaches taken by different teams. Some are purely on a circuit level trying to recreate a model and specifically what it's outputting. Others have, for example, gone the proof system approach of making special purpose proof systems that are specific for a type of classifier and a type of inference that's being made. But it's even like down to the substrate of saying, like, for instance, like there's been very little work that's done into finite field-based neural nets, for instance, and like using finite field representations is one of the cheapest ways. But of course, we know that these models are imprecise, and so the question becomes, how do I ensure that the lossiness of that behavior is captured in the arithmetics, and it still gives you a reasonable output? And I think that there's a lot we can still do to optimize on that representation itself.
Just on a super simple level, seems like compute is a bottleneck. If you could ZK prove everything, then sure, but you can't.
Compute is always the bottleneck. We're waiting for the singularity over here. But the practical reality is, I was offline, I was just discussing this with someone. We very quickly move from what is theoretically interesting to what is practically very useful, even with mild improvements in performance. Something we've seen, the example that Ismail gave on deep proof on the ZKML work that we're doing at Lagrange, we think we very, very narrowly crossed that barrier, where we went from something being, certainly academically very curious, but it would take an enormous amount of patience on the user side for that to be even entertained. Now it's become within striking distance of something that's useful. The question is, do we pursue that avenue as the highest priority, or do we ask ourselves, with the current state of cryptography, what can we do? I imagine, like most things, the answer is somewhere in between, where I'm sure we can unearth some practical applications with the sort of state of the art that we have, with the lingua franca that we have today. Or we can just do nothing for the next 2 years and just come back and ask the same exact questions. And I bet you would get a lot more interesting answers. So what do? We just stay around, idle, 2 years?
So I think it really depends on what use case you're going to use this technology for, right? So one of the examples that Ismail gave is what we're doing with yourselves on the healthcare use case. So it really depends on the industry, and certain industries which are regulated, which have this high, threshold of being able to prove and make sure that whatever outcomes are created through that has to pass a certain level. you need to make sure that this technology is always up to date. It is really pushing forward so that there is adoption there. Right? Because one of the things that we keep hearing or coming up against, and this is something that we'll start hearing a lot in the enterprise circles as well, is how do we not know that a particular outcome that was generated was hallucinated, right? So how do we know we can trust that, right? In real use cases, critical use cases where lives are at stake, millions are at stake, you need to be able to go back and say, this is exactly why a certain decision was made, and we can prove that this came from this particular source, right? In those cases, I think the technology will have to improve for real adoption to occur. So I don't think we should be sitting idle. We should really be pushing it ahead and really push adoption through that.
So speaking of hallucinations, one approach is just brute force. We can brute force our way out of hallucinatory dreams by repetition. That's one way to do it. That's very expensive. Is there a way to natively embed an anti-hallucination mechanism that doesn't come from the transformer architecture, but somehow leaks in from the ZK side?
I'm not sure. I'm not sure. Because for me, hallucination is a property of the model.
Exactly.
There's nothing wrong with it. I mean, you may not like it, but it's a property of the model. And so I'm not sure what you're trying to remove here. I mean, okay, you not like hallucinating model, and that's completely understandable. But that is what model is for. So you have to fix the model rather than say, okay, maybe some ZK would do the magic. I don't think that ZK is going to do the magic for you. It's a property of the model, in my view.
Well, let me rephrase it then. Suppose you had access to, let's say, multiple models, or suppose you had access to multiple private inputs that the individual user doesn't have access to. Remember, the individual user is susceptible to hallucinations, but 1,000 users could tell you more about these hallucinations than that one user. So you as a back end, in so much that you are privy to that, you can say something about these hallucinations. I was not referring to this in the same way that a coin flip is hypersensitive to perturbation. There's nothing that you can do with ZK in order to make that calculation better. But if I tell you now you're privy to the fact that 1,000 people have flipped coins, all of a sudden you can advise the user, or you can tell the user something they wouldn't know, and you can do that without A, leaking out privacy from all of the other data that you've accessed, and B, you can do that in a way that's trustless. The worst thing that can happen is if the model starts to hallucinate and you start to lie about it.
Sure. I mean, feeding back the data, of course, that's a good point. But I'm saying, like, it's a model issue. And what you're trying to say, what you're proposing is a way in which you would feed back the data back to the model in some way. But that's basically fixing the model, right? And you could do it with ZK, you can do it without ZK, right? Mm-hmm. ZK would give you privacy if you want to use the privacy angle to it. But still, it's fixing the model. It's not about...
ultimately, circuits don't hallucinate.
Yeah, exactly. Yeah.
Just one more, out of left field take is that we're kind of assuming that there are these LLMs of the variety that everyone talks about that are hallucinating in the way that we all think about. In the near future, right, we may have more agentic-like systems. We may have systems that have different inputs. They might have cryptoeconomic inputs. The AI could lose money if it hallucinates, and it could decide to behave in a different way so that it doesn't lose money, which is kind of the cryptoeconomic trust model. I think we haven't even begun to explore what you can do with that model when you constrain the behavior of these systems with financial penalization.
I think certainly you can account for these things in the penalty model. Again, to his point, it is a model problem. So we can start accounting for that, and we can put layers and layers upon checking. As simple as read what you just said. Like, do you know what you just said? Just feeding that back into the model tends to constrain it in a way that's non-trivial.
So I've seen systems, some people building systems where there's like a master agent or master model, then you have these...
A boss.
Yeah, and then you have these children or slave models. And so you as a user, you would, request an inference from this master model, then you kind of double check with these slave models. And if you slave models are saying, this guy is hallucinating, then you kind of feed it back in some way. So yeah, but again, the point is like they are trying to fix the model, and there are many ways of trying to fix the model, right? Which is in my view, it's a slightly different problem in my view.
Well, with that note, and with hopefully a few less hallucinations, let's thank our panelists, and we can go for some tea.
Thank you very much.
Thank you.
Of all the stories.